Imagine a world where AI doesn't just see medical images. It understands them, even when the data is noisy, incomplete, or unclear. Today, we're exploring how researchers are unlocking this potential using a groundbreaking approach: self-supervised learning with V-JEPA and 3D localization to revolutionize ultrasound imaging. Let's break down the science behind this breakthrough. Ultrasound is a cornerstone of modern medicine, safe, portable, and cost-effective. But here's the problem. Its images are often plagued by noise, low contrast, and artifacts like shadows or echoes. Traditional AI models require massive labeled datasets to learn, but manually annotating ultrasound videos is time-consuming and error-prone. That's where self-supervised learning, SSL, steps in. Think of SSL as teaching a child to recognize animals without showing them textbooks. Instead, the model learns patterns by itself, like noticing how a cat's tail moves differently from a dog's. In medical imaging, this means training AI on vast amounts of unlabeled ultrasound videos, letting it discover anatomical structures and motion patterns autonomously. The key innovation here is V-JEPA, a self-supervised framework that doesn't rely on pixel-level predictions or negative examples. Instead, it focuses on abstract features, like the temporal dynamics of a beating heart or the spatial relationships between organs. This makes it remarkably robust to noise, a critical advantage for ultrasound. But here's the catch. Even the best SSL models struggle with small datasets. Ultrasound data is often scarce, and standard models like vision transformers, VTS, miss fine-grained details. To solve this, researchers introduced a 3D localization task. Imagine teaching an AI to navigate a video sequence, predicting not just what it sees, but where structures are located relative to other frames. This spatial reasoning helps distinguish real anatomy from artifacts, even with limited data. Let's dive into the technical specifics. The team pre-trained V-JEPA on large video datasets, then fine-tuned it using Atom W Optimizer, a variant of stochastic gradient descent that adapts learning rates dynamically. They paired this with cross-entropy loss, which measures how well the model segments organs, and a cosine learning rate schedule to prevent overshooting optimal solutions. To evaluate performance, they used metrics like the Dice Similarity Coefficient, DSC, and Jaccard Index, which quantify how closely the AI's predictions match ground truth annotations. They also tracked precision, how many predictions are correct, and recall how many actual structures are detected. The results? Stunning. On the Camus cardiac ultrasound dataset, their method achieved an 8.35% accuracy boost over baseline models, even when trained on just 10% of the data. By freezing parts of the neural network during pre-training, a technique called feature freezing, they reduced overfitting, ensuring the model generalizes well to new cases. Here's why this matters. Traditional supervised models require thousands of labeled images, but this approach works with far less. This could democratize medical AI, making high-quality diagnostics accessible in resource-limited settings. So what's the takeaway? By combining SSL's pattern recognition with spatial reasoning, researchers are creating AI that's not just accurate, but adaptable. As this technology matures, we could see real-time, high-precision ultrasound analysis without the need for massive datasets. Thanks for watching. If you're curious about how AI is reshaping medicine, hit subscribe for more deep dives. And drop a comment, what medical tech excites you most? Until next time.